Titanium is not rare. It's the ninth most common element in the entire crust of the Earth. More abundant than copper, more abundant than tin, more abundant than lead. There's titanium in the dirt outside your door, in beach sand, in the paint on your walls. And yet a block of pure titanium costs many times more than the same block of steel. Something doesn't add up. If the stuff is practically everywhere, why is it so brutally expensive to actually get? The answer is that titanium is a control freak. It refuses to let go of oxygen, and prying it loose takes one of the most stubborn, violent, slow industrial processes we still run, almost unchanged since the 1940s. Start with where titanium comes from, because it's not some deep, guarded mine. It's in ordinary ground. Titanium almost never shows up as pure metal in nature. It's always locked to oxygen as titanium dioxide in two main ores, rutile, and a darker iron titanium mineral called ilmenite. This is the same titanium dioxide that makes white paint white, makes sunscreen white, makes the inside of an Oreo white. You have eaten titanium dioxide. It's that common. So mining isn't the hard part. Companies dredge it out of mineral sands, the heavy dark grains you sometimes see streaked across a beach. The raw material is cheap and plentiful, which makes the price tag even stranger. If the ore is basically sand, where does all the cost come from? It comes from one problem: getting the oxygen off. Here's the core of the whole story. Titanium and oxygen love each other, not casually, violently. Titanium forms one of the strongest, most stubborn bonds with oxygen in all of chemistry. Once they're joined, that bond does not want to break. Compare that to iron. Iron holds onto oxygen too. That's what rust is. But iron gives it up relatively easily. Blast iron ore with heat and carbon, and the oxygen leaves, and you get metal. That single easy reaction is why we've made iron and steel for thousands of years, cheaply, by the ton. Try the same trick on titanium, and it backfires. Heat titanium ore with carbon, and the titanium doesn't cleanly let go of the oxygen. It just grabs the carbon too, and makes a rock-hard, useless titanium carbide. You can't smelt titanium the way you smelt iron. The obvious cheap method is off the table. So to win, you can't fight the oxygen head-on. You have to trick the titanium into bonding with something else first. The trick starts by getting the titanium away from oxygen and onto a different partner entirely, chlorine. The ore is loaded into a tall reactor, mixed with carbon, and blasted with chlorine gas at around 1,000 degrees Celsius. In there, the titanium trades partners. It drops some of its oxygen and grabs chlorine instead, forming a new compound called titanium tetrachloride. One titanium atom, 4 chlorines. Titanium tetrachloride is a colorless liquid that fumes violently in open air, and it boils easily into a gas. Engineers actually love that because the gas is easy to purify. They distill it exactly like a refinery separates fuels, until what's left is titanium tetrachloride, so clean it's almost surgical. Nickname on the factory floor? Tickle, from the letters TICL. So now we have ultra-pure titanium, but it's still shackled, just to chlorine now instead of oxygen. We've swapped one jailer for a weaker one. Now comes the part that has barely changed in 80 years. This is the step that makes titanium expensive. It's called the Kroll process, invented by William Kroll in 1940, and we still basically do it his way. Take that purified titanium tetrachloride and pour it into a sealed steel reactor filled with molten magnesium, liquid metal, glowing hot, with every trace of air pumped out and replaced by inert argon gas. Why the paranoia about air? Because if oxygen got in, the titanium would instantly grab it and we'd be right back where we started. Inside that sealed vessel, magnesium is the hero. Magnesium wants the chlorine even more than titanium does. So the magnesium rips the chlorine right off, freeing the titanium at last as pure metal. This reaction runs hot and hard for days. Not minutes, days. And here's the killer detail. The titanium that comes out isn't a neat bar. It forms as a gray, porous, crusty mass, full of holes, riddled with leftover magnesium and salt. It genuinely looks like a metal sponge. So that's the actual industry name, titanium sponge. When the days are up, they crack open the reactor, pull out this giant sponge, and clean out the trapped salt and magnesium. Then they do the whole thing again from scratch, one batch at a time. Stop on that word, batch. This is the hidden reason titanium costs what it does, and it's easy to miss. Steel is made continuously. Molten iron pours out of a blast furnace in a river, all day, every day, never stopping. That non-stop flow is exactly why steel is cheap. Continuous means fast, and fast means cheap. Titanium can't do that. The Kroll process is a batch. You load the reactor, you seal it, you wait days, you crack it open, you dig out a sponge, you clean it, and only then can you start the next one. There is no river of titanium. It comes out in slow, separate loads, like baking one enormous loaf of bread at a time in an oven that takes a week per loaf. Now add up the bill. Enormous energy to run everything molten and hot for days. Expensive magnesium and chlorine, carefully recycled. A totally sealed argon-filled, air-free environment. And that slow, one-at-a-time rhythm that no amount of scale fully speeds up. Cheap ore, brutally expensive process. That's the whole paradox, and we're not even done, because the sponge still isn't a usable object. That sponge is pure titanium, but it's a crumbly, holy mess. To make anything, a jet part, a hip implant, you need a solid, uniform block. So there's yet another expensive step. The sponge gets crushed and pressed, often blended with other metals to make an alloy, into a big compressed electrode. Then it's melted in a vacuum furnace, using an electric arc. And here's the thing, it has to be a vacuum. If you melted titanium in open air, the molten metal would instantly inhale oxygen and nitrogen from the atmosphere and turn brittle and ruined. That control-freak chemistry never quits, not even at the finish line. Everything, right to the end, happens sealed away from air. Out of that vacuum melt comes a clean titanium ingot, a solid cylinder of metal. And often, they melt it twice, sometimes 3 times, to make sure it's perfectly uniform, because a hidden flaw in a jet engine part is not an option. Only now, after mining, chlorinating, Kroll, cleaning, pressing, and vacuum melting, do you finally have titanium you can forge and machine into a real part. After all that, why does anyone pay for it? Because titanium's properties are genuinely spectacular, and for some jobs, nothing else comes close. First, the strength-to-weight ratio. Titanium alloys are nearly as strong as many steels, but titanium is about 45% lighter. Roughly the strength, a little over half the weight. For a jet, a rocket, or a bike frame, that ratio is everything. Second, and this is the beautiful part, corrosion. Remember titanium's obsession with oxygen, the thing that made it so hard to purify. That same obsession becomes a superpower. The instant a titanium surface meets air, it grabs a microscopically thin layer of oxide and seals itself shut. That invisible skin is chemically tough and self-healing. Scratch it, and it reseals in a heartbeat. That's why titanium shrugs off salt water, acids, and the inside of the human body. The very flaw is the feature. That combination, light, strong, and basically immune to corrosion, is why titanium goes exactly where failure is catastrophic and weight is precious. Jet engines and airframes, deep-diving submarine hulls, ships, and medical implants like hip joints and dental screws that live inside you for decades without corroding. So, it's a wonder metal. But let's be honest about the catch, because titanium is a genuine pain, and the price is only the start, the cost. We just walked through why. A batch process, days per load, enormous energy, everything sealed from air. That's baked in. Titanium will likely always cost many times what steel does, not because the ore is rare, but because the process is stubborn. Machining it. Titanium is hard to cut. It's strong. It doesn't shed heat well, so all that cutting heat piles up right at the tool edge and chews through cutting tools fast. Machinists run slow, flood it with coolant, and still burn through bits. Slow and finicky means expensive to shape. Welding it. Remember, it inhales oxygen and nitrogen when hot? So you can't just weld titanium in open air. The weld would go brittle and fail. You have to shield the hot metal in a bath of inert gas the entire time it cools. Doable, but demanding and costly. So the real question isn't, is titanium the best metal? It's, is this job worth the price and the hassle? For your car bumper or a bridge? Absolutely not. Steel is cheaper and plenty good. But for a jet engine spinning at the edge of physics, or a bolt that has to live inside your body for 30 years, titanium's price is a bargain. You pay for it exactly where nothing else will do. So let's put the paradox to bed. Titanium is not expensive because it's rare. It's the 9th most common element in the ground, sitting in beach sand and paint. It's expensive because it's a control freak that clamps onto oxygen and won't let go, forcing us to swap the ore into a gas, then batter the chlorine off with molten magnesium inside a sealed, airless reactor for days, one slow batch at a time. Then melt the sponge in a vacuum so it can't grab oxygen back. Cheap dirt, brutal process, and the same clinginess that makes it a nightmare to purify is exactly why the finished metal is so good. Why it seals itself against rust and salt water and won't corrode inside your body. The flaw and the superpower are the same trait, just pointed in opposite directions. That's titanium. Everywhere and hard won. Subscribe to Whambox for more how does it actually work explainers.